Welcome back to ECE 501B. Homework number 4 is due on the 19th of October. And I did finally today post the additional sort of write-up, maybe 6 pages on how you can find eigenvalues and eigenvectors, or a strategy for doing that without having to use the determinant, which is in chapter 10 of this book. But you might look at that and make sure there is an example in that particular discussion at the end, and that should help make it a little bit more clear rather than just the generic development or the general development. We're going to continue today with talking about eigenvalues and eigenvectors, which is chapter 5. We will recap the definition of eigenvalues and eigenvectors. You should have that memorized by now. You should be waking up in the middle of the night and saying ax equal lambda x or something to that effect. Then we will continue with chapter 5 and talk about when can we expect to have linearly independent eigenvectors. And if you now have distinct eigenvalues, distinct meaning non-repeated, or meaning you have lambda 1 is different from lambda 2, it's different from lambda 3, then those 3 eigenvalues would have linearly independent eigenvectors. And that's what we'll show or prove in theorem 5.6. Then we will just state corollary 5.9, which basically says that the number of distinct eigenvalues is obviously less than or equal to the dimension of your vector space that the operator is operating on. If your vector space V is little Nevada in size, then you can expect to have no more than Nevada distinct eigenvalues. That, I hope, is clear. We will just again mention that now that we have this idea of maps or a linear operator, we can combine those so that we can now have the map squared or the map cubed, which allows us now to create polynomials in matrices. And with that, we can start to express polynomial expansions of more complicated functions of a matrix. And we'll show what that means, or what that looks like maybe for e to the a. What's it mean to exponentiate a matrix? A is now no longer a scalar. A might be this Nevada by Nevada matrix. Then we will talk about every finite dimensional complex vector space of dimension greater than 0. So that means we have some v that's 1 or bigger in terms of the vector space. That I should say every operator on a finite dimensional vector space of dimension greater than 0 has an eigenvalue. So I left out some words there, but we should say that every operator on a finite dimensional complex vector space of dimension greater than 0 has an eigenvalue. And then we will talk about nice matrices or nicer matrices, which means that we want some zeros, and it would be nice to have those zeros in particular locations, and that's then motivating this idea of an upper triangular matrix. That leads to nicer matrices. As a recap, here is what we know, or what we've been talking about: eigenvalues and eigenvectors. And when you hear an eigenvector, I want you to almost immediately start thinking an invariant subspace. That gives you a different way of thinking about eigenvectors. For some reason, now when we start in that direction, if we operate on it with this linear map, we stay in that direction. That's an eigenvector. Those are what we are then talking about now, and what can we learn more facts about these eigenvalues and eigenvectors. If this equation is true, TW equals lambda W, then we know that lambda is our eigenvalue and W is our eigenvector. Here is the example that we really just started on last time that we were together, and it represents a 90 degrees counterclockwise rotation in the xy plane. The linear map takes this 2-vector W1, W2 and maps it into minus W2, W1. If you view the first coordinate and the second coordinate like the x and y direction, hopefully you can see this 90 degree counterclockwise rotation in the xy plane. From that equation in the middle of the screen on the right, minus W2, W1 equaling lambda W1, lambda W2, that now leads to this equation that lambda needs to satisfy. We need lambda squared to equal minus 1 based on this linear map. That's sort of where we made it to last time. I want to just quickly scroll through the two possible solutions. If we restrict our field of numbers that satisfy this equation to be reals, then there is no solution. We can't find a real number when we square it and end up with minus 1, which means that this particular linear map does not have real eigenvalues. No invariant directions. If we don't have eigenvalues, we don't have eigenvectors, which means, oh, we don't have invariant subspaces for this rotation map. That's one example of a map, a linear map, on the real number field that does not allow real eigenvalues. So that rotation does not preserve any directions. It's rotating. So instead of sticking in one direction, you're rotating in space, and that's obviously then not an invariant subspace, or an invariant subspace does not exist. If we allow the field of numbers that we are playing on to be complex, then we can solve lambda squared equal minus 1. That's why we invented complex numbers, or that's why we have complex numbers, to allow solutions to such equations. We now know that lambda can be either plus j or minus j, where j is the square root of minus 1. And that will then solve lambda squared equals minus 1. Those are our eigenvalues, plus and minus j. And the visual that I want you to maybe think about is if you were looking at, well, another class, you could think of, oh, let's say that I now have a complex plane, and typically that might be the S-plane if you were doing Laplace transforms. Now my poles, or eigenvalues, are at minus j and plus j. They're on the imaginary axis, where this is now the real component, and this direction is the imaginary component if S were, let's say, the set of complex numbers. And now lambda is a complex number. It's plus j and minus j. What we want to do now is associate the eigenvector, or the directionality of that linear map, with respect to these scalars. Remember, these scalars are scaling our movement. When we apply the linear map, these eigenvalues are scaling in a particular direction. And now it's maybe a little bit more confusing, because now we will end up with directions that might be complex, meaning, and what, well, how do I, let's just continue. So now we need to find our eigenvectors. We should have, and here, just to sort of play the tape in advance, or to give us a little bit of forward thinking, lambda being equal to plus and minus j, those are distinct eigenvalues. We have one at plus j and one at minus j. Those are considered distinct eigenvalues. They're not on top of those x's are not lying on top of each other. One's in the upper half and one's in the lower half of our complex plane. What do we have in terms of direction when we have lambda equal to the plus j? So this first case I, is now when we're dealing with that eigenvalue. That's the scalar that's scaling our direction, our eigenvector. If we now use that lambda in our eigenvalue-eigenvector equation, now W1 and W2 represent the first component and the second component of our eigenvector. We now have TW is equal to lambda W. That gives us minus W2 W1 is equal to J times the original W, which is W1 W2. We push that J through to each component, and now we get two equations from each component of our equation. But if you look at those, we have some redundancy, or they're dependent, and that should be okay. That should make you think, oh, that's all right, because we needed a non-trivial vector in our null space of this equation. So we should have had some redundancy in our equations. We would have two equations. But if that's the case, let's now play with the red equation, or the first component, that says the eigenvector has to have this particular relationship between coordinate 1 and coordinate 2 in that eigenvector. W1 times J is supposed to equal minus W2. Let's solve for W2 and then just assume that W1 is our free variable. And W1 is playing in the field of complex numbers. So the second coordinate of our eigenvector is a scalar away from the first coordinate. It's just minus J times the first coordinate. Or the eigenvector, which was this one, which is associated with the eigenvalue of plus J, can now be written as W is the first coordinate, W1, and the second coordinate is W2, which we just found is minus J, W1. You now take W1 as a complex number, and that gives you your eigenvector associated with the eigenvalue of plus J. What does that say? That says if you start with a vector, let's just pick W1 equal to 1. You now have a vector of 1 and minus J. That's your vector. Those are the components of your vector. Now, when you operate on that with this linear transformation, you're going to stay in that same direction. It's just going to be scaled by plus J as your scalar. That's what this is saying. If we now look at the other eigenvalue, we had two distinct eigenvalues. We can do the same analysis, except now we're using a scalar of minus J. That's now our eigenvalue. This now produces two equations that are equivalent. Let's just look at the first coordinate in that two-coordinate equation, and we get minus W sub 2 is equal to minus J omega sub 1. Or multiplying by minus 1, we see that the second coordinate is J omega 1. This is now the eigenvector W1 J W1 for the eigenvalue at minus J. And that's what I was hoping you would go home and do after the last lecture, is to derive that, or try to find those eigenvectors associated with those eigenvalues. So let's now start with this theorem, theorem 5.6, which says that the eigenvectors, now that we've looked at a couple of different ways of finding eigenvalues and eigenvectors, the eigenvectors associated with distinct eigenvalues of the linear map T, those eigenvectors are in fact linearly independent. And we should see that this W is linearly independent from that W. The second coordinate is the negative of the second coordinate in the second one. So those are linearly independent vectors. That is an example of the application of this theorem, theorem 5.6. Let's see if we can show or prove that, in fact, the eigenvectors associated with distinct eigenvalues of a linear map are indeed linearly independent. We have this linear operator. T is a linear operator on V. Let's assume that we have Michigan eigenvalues, and these are distinct. We might actually have Nevada for our dimension, but now we're just showing that if we have, let's just assume that we have Michigan distinct eigenvalues. We might have some eigenvalues that are repeated. But for these that are distinct, we need to show that the corresponding eigenvectors for these eigenvalues are indeed linearly independent. If that's the case, then let's just associate some eigenvectors with respect to those eigenvalues, and these are then the associated eigenvectors. Lambda 1 is associated with V1. V1 is a vector, and it could be a vector that has Nevada coordinates. It doesn't have to have M coordinates. We're not assuming that all of the eigenvalues in this linear map are distinct. And that's what I'm going to say here. Let's note that M, Michigan, is less than or equal to N, where N is the dimension of our vector space, V. And to show this, let's prove it by contradiction. So now we're saying that the eigenvectors associated with distinct eigenvalues of T are linearly independent. Let's assume that those M eigenvectors are in fact dependent for our proof by contradiction. Let's now assume V1, V2 through V sub M, that set or that list is linearly dependent. What does it mean if we have vectors that are linearly dependent? What are some statements we could make if I tell you V1 through Vm, that list of vectors is linearly dependent? What's a statement that you could make? Okay, so one of those vectors could be represented as a linear combination of some of the others. Not all of them, but some of them. Or another way of saying that is one of those vectors is in the span of all of the others. Is that okay? So that's what I am going to say. Let's say that that statement, that this list of vectors is linearly dependent, that means at least one of those vectors is in the span of the others. And now let me make something that might seem a little bit odd, but I'm really trying to sort of order these. So now let's let this index L, that's a lowercase l, let L be the smallest integer such that the vector v sub L, so L is obviously between 1 and Michigan, 1 and M, such that v sub L is in the span of v1, v2, v sub L minus 1. So we know that one of these vectors, at least one, is in the span of the others. Now we're ordering those vectors such that when we walk through all of those vectors, v sub Louisiana is the first one that we come to that we can write in terms of the previous 1 through L minus 1. Is that clear? That's just sort of an ordering of the eigenvectors, and now let's just assume that L is the smallest integer such that we could do that. If v sub 2 could be written in terms of v sub 1, or as it was in the same direction, then little l would be 2. And then it would be in the span of v sub 1. That's all I'm saying. That just sort of gives us some vectors to play with. And this has to be true. L could be Michigan. All right. So now this is getting back to the comment from before, but now we have some indices to play with. This means we can write the vector v sub L as a1 v1 plus a sub 2 v2 plus a sub L minus 1 v sub L minus 1. That's what we mean by v sub L being in the span of those earlier v1 through v sub L minus 1s. And that's what the comment was before, or the statement. That's now a true or a given equation based on the fact that that list of vectors is linearly dependent. We can create this equation. We can find A's such that this is true. And again, the V's are just vectors, but they're special vectors. Why are they special? Those are eigenvectors. Well, if they're eigenvectors, let's now apply our linear map to that, both sides of this equation. Let's now apply T to both sides of that equation so that I now have T v sub L is equal to, and I'm going to slide those scalars to the left of the map. I have a1 T v1 plus a sub 2 T v sub 2 plus a sub L minus 1 T v sub L minus 1. And now I'm going to end up with my first equation that I want to play with. What do we know T v sub L is also equal to? Remember, v sub L is an eigenvector, and we paired it up with lambda sub L, which means that T v sub L we could rewrite as lambda v sub L. And we can do the same thing or a similar thing to all of these TV1, TV2, etc. They now collapse to a scalar times V1, a scalar times V2, etc. Where that scalar is lambda 1, lambda 2, etc. Or this is now A1, lambda 1, V1, plus A sub 2, lambda sub 2, V sub 2, plus a sub L minus 1, lambda sub L minus 1, v sub L minus 1. We were able to do that because of the eigenvalue-eigenvector relationship. Here's the explanation. This is since T v sub I is equal to lambda sub I v sub I. Is everybody comfortable with 1? Now we also know, or we can return to our equation for v sub L. We've written that as a1 v1 plus a sub 2 v sub 2 plus a sub L minus 1 v sub L minus 1. We know that's true. Now the second equation that I really want is, let me now multiply both sides by lambda sub L. Whoops, you guys should have slowed me down. This should be lambda sub L v sub L, right? In equation 1 on the left, that was t v sub L, so that should correspond to or be in the direction of v sub L, but with a scalar of lambda sub L. Let's now multiply this equation in blue at the bottom by lambda sub L, which gives us equation 2, which says now this is lambda sub L v sub L is equal to a1 lambda sub L v1 plus a sub 2 lambda sub L v sub 2. Since we're multiplying both sides by lambda sub L, now we get the second equation. And what we want to do now is see that the left-hand sides of equation 1 and equation 2 are identical. Let's now compare, or basically compare 1 and 2, or subtract equation 2 from equation 1. And then we end up with what on the left-hand side? If we now combine equation 1 and equation 2 by subtracting 2 from 1, I'm going to now say I'm producing equation 3, which now gives me 0 on the left, since that was lambda sub L v sub L in both equations. I have a common a1 and a common v1 in the first term, but I have a difference in my lambdas. Or now I have an a1, I have a lambda 1 minus lambda L v1 plus an a sub 2 lambda sub 2 minus lambda sub L v sub 2 plus an a sub L minus 1 lambda L minus 1 minus lambda sub L v sub L minus 1. Now we can actually use the fact of why did we order those eigenvalues in this particular way to begin with. We said, let's let v sub L be the first eigenvector that can be written in terms of a linear combination of the previous L minus 1 vectors. What do we have on the right-hand side? We have all of our previous L minus 1 vectors, and they are somehow combined to give us 0. And how are they being combined? By coefficients or by scalars. We have an a1 times a scalar. We have an a2 times a scalar. So let me write down what I'm trying to say. Because the vector v sub L was the first, by definition of how we ordered these vectors, because v sub L was the first vector, that could be written in terms of the earlier vectors, the list v1, v2, v sub l minus 1 must be linearly something. Is it dependent or independent? We said v sub l was the first vector that would become linearly dependent on the previous vectors. These all have to be linearly independent. So these are all linearly independent. If that's the case, what does equation 3 tell us? Now we have a linear combination of linearly independent vectors equaling 0. What do you know about vectors if they're linearly independent and you try to combine those with scalars? What do you know about those scalars? All the coefficients have to be 0, right? So now we need a1 times lambda 1 minus lambda sub l. That has to be 0. We need a sub 2 times lambda sub 2 minus lambda sub l equaling 0. Since it's a product, we can make that 0 happen two different ways. We could either make it happen by making the lambdas the same, or we could make the a's the same. Or, I'm sorry, the a's 0. Let me write that down. So now, therefore, equation 3 implies, so here let me get caught up, 3 implies all the coefficients are 0. That is a sub 1 lambda 1 minus lambda sub l is equal to 0, etc., with a sub 2, lambda 2, etc. And we can make that happen in a couple of different ways. Therefore, the first case, either there are non-distinct eigenvalues, meaning we're setting those lambdas, lambda 1 equal to lambda L, lambda 2 equal to lambda L. So we have some repeated eigenvalues, and that's actually a contradiction. We were assuming that all of our eigenvalues, or these first m ones, were distinct. And now we've shown or said one possibility might be that we do have some repeated eigenvalues. Well, that's a contradiction. And that's what we were looking for. We were trying to prove this by contradiction. So we've found that that particular path leads to a contradiction. The next path for all of those coefficients to be 0 would be that all the, let's say, a sub j's are 0. So now let's see if we can come up with a contradiction if we make that assumption. If all the a sub j's are 0, now we need to go back and remember what v sub l looked like. V sub l was now some linear combination of the earlier v's, but we use those a's to make that combination. Well, if all of those a's are 0, what do we know about v sub l? If these a's, a1, a2 through a sub l minus 1, are all 0, what does that give us for v sub l? 0. And that's not what we started with. We said it's now what? It's in this set of vectors that are linearly dependent, and we didn't allow any of those to be 0. So now this fact that V sub L is A1 V1 plus A2 V2, that's how we originally found all of these A's. If all of those A's are now 0, then that would imply that V sub L is 0, and that's a contradiction. So now we have exhausted all of the possibilities in our strategy for trying to come up with a way of contradicting our original assumptions, so that our assumption was that V1, that linear list of vectors V1 through V sub m, was linearly dependent. Now we know that that can't be the case. In fact, those are V1, V2, V sub m, must be linearly independent. And that says then that once you start with distinct eigenvalues of a linear map, the associated eigenvectors from those distinct eigenvalues will be linearly independent. And that now allows us to start spanning different spaces if we want to. Now, let's look at the next corollary that I'm just going to state, which is corollary 9 in the second edition of chapter 5. Suppose T is an operator on V, then that linear map T cannot have more than dimension of V distinct eigenvalues. And I'm just going to refer you to the textbook for that. But that sort of, I hope, makes some intuitive sense. We can't have more eigenvalues than we have dimension of our vector space, and consequently we can't have more than in Nevada distinct eigenvalues. We know that the dimension of our vector space is going to influence the maximum number of eigenvalues that we might have. And that maximum could be as many as n, or Nevada, if our vector space that we're starting with is Nevada in size, r to the n. We can have at most n eigenvalues. They don't all have to be distinct, and so we can only have at most n distinct eigenvalues. But we could have, let's say that Nevada was 4. Maybe we have 2 distinct eigenvalues. Maybe we have repeated eigenvalue 3 and eigenvalue 4. Maybe 3 is the same as 2 and 4 is the same as 1, for example, in terms of eigenvalues. Those are some facts. Now let's talk a little bit more about what we can build with those facts in mind. And this is now powers, polynomials, and functions of these linear maps, which are now specialized to the domain and codomain being the same, so now they are operators. And we're going to utilize that fact. Since an operator is a map, from a vector space back to itself, then repeated applications of that linear map are well defined. Meaning, if we now take this linear map T on the vector space V, let's establish some notation. We'll define, if somebody says, oh, I have that linear map raised to the mth power, that's now really saying, oh, T is applied to T is applied to dot, dot, dot is applied to T, Michigan times, little m times. That's what we mean by T to the mth power. We're just applying that map repeatedly up to m times. And just to make sure our notation is clean, if somebody now gives you the linear map raised to the 0th power, we will define that. What if I gave you 5, the number 5, raised to the 0th power? What is that? 5 to the 0, 1. What if I give you 7 to the 0, 1? So now I'm giving you a matrix, raising it to the 0th power. What would you expect that would be? It's now the identity matrix. So we're defining T to the 0th power to be the identity matrix. If that linear map is on the vector space of n size, Nevada size, now we have an n by n identity matrix, or an identity map. Now, with this definition of linear maps to powers, we can now take T to the 0, T to the 1, T to the m. Let's now use that with this. We can define polynomials of operators. By that I'm meaning, suppose that somebody gave you a polynomial p of some function z, or I'm sorry, of some variable z, where that polynomial was a scalar a sub 0 plus a1z on up to, let's say, plus a sub m z to the m. What that now allows us to say is, if we now wanted that polynomial of the linear map, now we take the scalar a sub 0 and scale our linear map to what power? What is the number right here? Z to the 0, isn't it? So this is now z to the 0, and what did we say? Now we're replacing t, our linear map, or we're replacing the z's everywhere in this polynomial with the linear map t. And we agreed that t to the 0 was the identity, so now we have a sub 0 plus the, or times the identity plus a1t etc., plus a sub m t to the n. That's how we can now express a polynomial of a linear map. Given a polynomial, you can now produce a matrix polynomial, or a linear map in terms of polynomials. And once we have those, now we can get creative. Because how have we maybe defined complicated functions before? If I gave you cosine of x, maybe you expand that in some Taylor series. If I give you sine of x, you could write that as some Taylor, and that gives it to you in terms of a polynomial. Instead of saying, oh boy, what's the cosine? Well, let me write that in terms of a polynomial. Or what's the sine? So once we have polynomials, we can even start talking about more complicated functions of operators. Meaning, if we're given some f of z, let's say that is some complicated function, think sine or cosine or something that's not just a polynomial, then we can say that f of t, that complicated function of the linear map, will now be represented in terms of a polynomial of that linear map, where now this p of z we could use to describe or express f of z in terms of a Taylor series expansion, and that now gives us powers of z. Now that consequently gives us linear maps raised to higher and higher powers, or an expression of that is the Taylor series expansion of the complicated function f of z. Let's look at an example that's used all the time or comes up a lot. Suppose we're given a linear map T that's an operator, and it's operating on some vector space V. And now suppose that somebody says, oh, my complicated function, f of z, I want that to be e to the z. This is now an exponential. Do you remember the Taylor series expansion for this exponential? Did I hear 1 plus z? Ooh, my 2 are z squared over 2 factorial, which is 2, right? I could have quit. Plus z cubed over 3 factorial, etc., in that same pattern. Now we know how to find the exponential of a matrix, or of a linear operator, or of a linear map. It's really a linear operator because we're restricting our domain and codomain to be the same. Now, if somebody says, oh, what's e to the t? What's the exponential of that operator? t, that's now, what's my first term? Now that 1 is equivalent to z to the 0, isn't it? So this is now t to the 0, which is the identity. And how big is that identity matrix? What's the size of the matrix representation of t? And now any answer is correct because I didn't tell you what the linear map was. I didn't define the dimension of V, did I? But generically, I say it's Nevada. So now if our linear map, our linear operator is operating on a vector space that's of dimension n, Nevada, then that identity matrix is what size? Nevada by Nevada. What's my next term in this Taylor series expansion for this matrix or this exponential of a matrix? T plus, and now that 1 over 2 factorial is just a scalar times t squared plus 1 over 3 factorial, another scalar, t cubed, and that just keeps going. There are more efficient ways to compute that rather than to continue to raise a matrix to a higher and higher power. We're not going to go into that now or some other time, but that usually really vanishes quite quickly, the higher ordered terms. But this exponential of a matrix is used a lot. And one of the places that it's used is in control, where we might have this state transition matrix. You might hear that used. So this is used heavily, let's say, in advanced topics. For example, control, and maybe even some quantum mechanics. If you're playing with quantum mechanics, you might need to find the exponential of a matrix. That was sort of an aside, but now we have a way of playing with these powers of linear operators. We know how to play with those to produce important expressions for maybe complicated functions. Let's go back to chapter 5 and some more facts. Here's a theorem. Theorem 510. Every operator on a finite dimensional, and now this next word, you can't leave that one out, complex vector space. We're not talking about a real vector space. Now we've expanded that notion to be dealing with complex vector space. And if you're tweeting this, that's FDC VS. If we have an operator, or for every operator on a finite dimensional complex vector space of positive dimension, of dimension greater than 0, every operator has an eigenvalue. That's pretty nice, or that's pretty powerful. You give me an operator on a complex vector, finite dimensional complex vector space, and we're guaranteed that that will have at least one eigenvalue. Let's see if we can show where that's coming from. Now let's say that we're given a complex vector space. And we'll call it capital V. And now let's have the dimension of that complex vector space be Nevada, where n is 1 or bigger. it's positive. That's our vector space, but this was talking about operators. Let's now identify an operator and call that T. And now let's select or choose a non-zero vector in that complex vector space. Let's now choose V in V, where V is not the zero vector. And this, we're just choosing an arbitrary vector in our complex vector space other than the zero vector. Now let me create a list. The list V, TV, T squared V, T to the N V. What can you tell me about the independence or dependence, the linear dependence or linear independence of that list? Can we say anything about the linear independence or dependence of that list? How many vectors are in that list? And now we have to kind of go back to our counting days and realize that that very first element, or that very first vector, is sort of the zero coordinate in that list. We have t to the 0, t to the 1, t to the 2. So we have 0 and little n more vectors, right? So how many vectors are in that list? N plus 1. And what do we know about the dimension of that vector space? The vector space is of dimension n. Now I give you n plus 1 vectors in that vector space. What do you know about the linear independence or linear dependence of those n plus 1 vectors? Are they dependent or independent? Dependent. If I give you 5 vectors in a 4-dimensional space, you know that you have some dependencies among those 5 vectors. So this list of n plus 1 vectors must be linearly dependent. Since you told me it has length, the list has length n plus 1, and the dimension of our vector space V was only n. Now let's write down an equation with those n plus 1 vectors. Thus, if we write 0 is equal to a sub 0 v plus a sub 1 t v plus a sub 2 t squared v up to a sub n t to the n v. What do we know about the a's? So now we have at least one of those being non-zero, right? But we can write one of those as a linear combination of the others. So we really kind of have a set of non-zero a's. So let's say that now from this, thus if we write this equation, which has n plus 1 terms on the right, we now have n plus 1 coefficients, we can find a set of complex A sub L's that are not all 0 that satisfy that equation or that make this equation true. Does everybody buy that? So now I can find some A's that are non-zero that allow me to set that equal to 0 with these n plus 1 vectors. Let's pick an M that's maybe not little n. So now I'm dealing with Michigan and Nevada. Let M be the largest integer such that A sub M is not equal to 0. So now we go up there in this equation and we find the biggest A that's not 0. And every A beyond that is 0. So we find the largest coefficient that's non-zero in this equation. And that's defining Michigan, or M. So if little n is 7, maybe M is 5. And then the other ones beyond 5 are 0. Remember what we assumed. We assumed that we were starting with a non-zero vector in our vector space. So since v was not equal to 0, then a1, a2, up through a sub m cannot all be 0. If every one of those coefficients, a1, a2, and this is all of the coefficients beyond a sub 0, if all of those were 0, then we would have a mess. So here is what I'm trying to say. A1 through AM cannot all be 0 since that would force A sub 0 to equal 0, since if we look at this equation, if A1 through A sub m are 0 and AM through A sub n are 0, the only term you have on the right-hand side is A sub 0v. But that's supposed to equal 0, and v is non-zero, so A sub 0 would have to be 0 if A1 through A sub m were 0. Is that making sense? Since that would force A sub 0 to equal 0, and we know the n plus 1 vectors are linearly dependent. That now says, so m is bigger than 0. That's the first that's the largest A that's non-zero. So it has to be 1 or bigger, little m, Michigan, which is less than or equal to n. This is a strict inequality. Now that we have that, now we can form a polynomial. We can use these A sub j's to create or write a polynomial. meaning we now have identified these a's, so let's now build up this polynomial p of z using those a's and a variable z, which is a sub 0 plus a1z plus a sub 2z squared up to a sub m z to the n. Oh, wait a minute. What did we have? Let's go ahead and create that polynomial to be all of these up through a sub n. So now let's keep this there. Now we're going to go back to our knowledge of polynomials, which we're assuming that you are experts on from Chapter 4, since we spent weeks on Chapter 4, but you now have to go back to Chapter 4 if you don't remember. What do we know about any polynomial of order n with complex coefficients? Needs to have at least a root, and we're actually going to have n complex roots, aren't we? So now from Chapter 4, any polynomial of order n with complex coefficients has n complex roots and can be factored into n terms. And that's true only because we're dealing with complex coefficients, complex polynomials, or the field of complex numbers. That's not true for real polynomials in general. So that now we have this polynomial p of z that we can factor. And the factors that we are going to have now, because we know that we only had, or m was our largest non-zero coefficient, we really are going to only have m factors in p of z when we factor it. So now we have z minus lambda 1, z minus lambda 2, up to z minus lambda sub m, because all of those coefficients higher than m were 0. Now, let's return to to t, our linear map. Now that we have a polynomial in z, we know that we have 0 is equal to a sub 0v plus a1 tv plus a sub 2 t squared v plus all the way up to a sub n t to the n v. That vector v is the same in all of those terms. Let's factor that out. So via additivity, we can write this equation. Zero is equal to a sub 0 plus, and now let me go ahead and put the placeholder in there since these are now maps or matrices. A sub 0I, a sub 1t plus a sub 2t squared plus a sub n t to the n times v. But what is that? That is actually what we defined right here for P of t. If we put in t for z, we would have this expression. It's those coefficients weighting the appropriate map, which is in this case t. But this is just P of t. But remember, P of z was here, and we could factor P of z to this, which means if this is P of t, we can factor P of t into a consistent factored form. This P of capital T we can factor, and we have 0 is equal to c times t minus lambda 1I, t minus lambda sub 2I, all the way up to t minus lambda sub mi times v. So now we have this product of maps that collapse to the 0 vector. And what happens when we have a map operating on a vector that goes to the 0 vector? What do we know about the, what are some descriptions? If I take a vector and I operate on it with a linear map, and then that combination goes to the 0 vector, what can I say property-wise is true about that map? Is it surjective? Is it not surjective? Is it injective? Is it non-injective? If I now take a map and I have a non-zero vector and that maps to the 0 vector, it's non-injective. I have a non-trivial null space, don't I? So now this says that one of those pieces in there has to be non-injective. One of these operators, t minus lambda 1, t minus lambda sub n. So this being 0 means that t minus lambda, I'll just say lambda sub ji, and you know that j doesn't mean the square root of minus 1, right? So I'm overusing, j is overloaded, j is now just an index. This, one of those maps is not injective, since that product drives me to the 0 vector for at least one of those lambda j's. Or another way of saying that, that is t minus lambda sub ji has a non-trivial null space. And if that's the case, then what do we know? If one of those t minus lambda sub ji's has a non-trivial null space, what's that going to say about that lambda sub j? If I have t minus lambda sub ji times a vector equaling the 0 vector, what's that say about that vector or that lambda sub j? What have we called that lambda sub j or vector at the beginning of class when we were recapping? That lambda sub j is an eigenvalue, isn't it? Because now we have a t minus lambda ji with a non-trivial null space. The vector in that non-trivial null space is an eigenvector. The coefficient or that scalar is the eigenvalue. So now we're saying that we have at least one eigenvalue for this linear map T, because that's what we've sort of concluded, that at least one of these lambda sub j's causes this linear map T minus lambda sub ji to have a non-trivial null space. Is that clear? So now this is saying, therefore, T has at least one eigenvalue. And you couldn't wait for me to draw that box. That's what we were trying to show. See? Saved by the bell. Somewhere. But I wanted to cover twice that much material. We'll have to pick up at some point really quickly with upper triangular matrices. But this now starts to give us more facts to play with relative to linear maps. We know about distinct eigenvalues and linearly independent eigenvectors. We know something about how many distinct eigenvalues we can have for a particular vector space. And now, if we're dealing with complex vector spaces, we know that we have at least one eigenvalue associated with that linear map. We'll pick up at that point next time.